Hello, good afternoon. Welcome to the second live session of Statistical Mechanics course, and I'm here to take all your questions, whatever questions you may still have, which have not been answered. And I hope you have been enjoying this course till now, and I hope you have been seriously working out the assignments as well. And if you still have any doubts about the details of the questions and the answers, you please ask me right now, and I will kind of send it to you at a later date. So I am ready to take any of your questions. So I hope you can hear me. So if you have questions, now is the time to ask. So please ask any questions that you may have. So if you can hear me, please ask questions right now. So type in your questions, we will answer them. So please ask questions about the tutorials or about any of the other issues that you may be facing. Are you able to listen to the videos? Is there audio problem? Are you able to understand my handwriting? Just ask any question that you want to ask. Now is the time to ask. So, there are only 4 of you who are currently watching, I think. So, if none of you have any questions, we might decide to wind up quickly. So, you please ask your questions right now. If you don't respond within the next few minutes, we are going to wind up. Can you type something? Don't just type something. So see if it's.
Does anyone have a question?
Just type something like, please ask your question. Okay, finally, there is a question. In an isolated system, does spreading energy take up energy? I mean to say, if I pour some amount of water at 10 degrees Celsius and 90 degrees Celsius together in a beaker, it will come to equilibrium at some time. So, that is the comment plus a question. So, I do not want to. Okay, so there is a follow up to that which says, will this process of mixing require energy? See, the point is that you should distinguish between two types of energy. One is the heat. So, the heat is directly converted to change of entropy. You see, in a reversible process, the heat that is pumped into the system is directly responsible for the change in entropy. So, if you remember dq, which is the heat change, that is the heat which is either extracted from the system or inserted into the system. If that is denoted by dq, then the change in entropy is correspondingly ds. So, so can I use my PPT right now? Okay, so yeah. Yeah, so this is a good question. So, let me spend some time trying to answer this. So, I am going to come back to your specific question about mixing a little later. So, let me straighten out some terminology first. So, when you speak of energy, you have to be very precise, because in physics, especially in thermodynamics and stat mech, there are so many different types of energy. There is a whole bunch of free energies, for example, Helmholtz free energy, Gibbs free energies. They are all energies, internal energy is an energy, and finally, heat energy is also an energy. So, there are so many different types of energy. So, you have to be very careful when you say energy, you have to say which energy you are talking about. So, suppose you are talking about heat energy. So, then you see the heat delta q. So, delta q is positive. Suppose we take the convention that delta q is positive, heat is flowing into the system, and delta q is negative if heat is extracted from the system, then this is directly related to TdS. So, you see the change in entropy. So, in other words, the change in entropy of the system is basically directly related to the heat that flows in and out of the system. So, this is one type of energy which is directly responsible for change in entropy. So, in that sense, heat is a kind of dirty type of energy, because what it does, it actually changes the entropy of the system. But there is a different type of energy which is called the internal energy. So, that is called delta U, that is a change in internal energy. So, so the point is that there is this first law of thermodynamics, which basically says that whatever heat that you pump into the system is responsible for doing two things. One is it increases the internal energy, also it gets work done. Part of it gets diverted to do work, part of it gets diverted to changing the internal energy. So, so in other words, you can't really so for an isolated system, the whole point is that delta Q is 0. So, for an isolated system, by definition is one where there is no heat flowing in or out of the system. So, as a result, the entropy of the system is constant. So, so the point is that so when you say mix, so that is of course you can't well, there is change in entropy. See that if you mix two systems, then you can't really, they are no longer isolated. Each subsystem interacts with the other subsystem. So, you can't really consider them isolated. So, then change in entropy is finite, it is not 0. Okay. So, coming back to your question, so let me read the question again. So the question says, so if you mix water at two different temperatures, it will come to an equilibrium, and will this process require energy? In the sense that so if you are asking should I do something actively so that it comes to an equilibrium. So, just waiting is not enough. So, I am assuming that is what you are asking. So, what I would do is that I mean common sense dictates that if you take a glass of hot water and pour it into a glass of cold water and you just wait long enough, it will definitely come to an equilibrium. So, so you do not really have to intervene actively, you do not have to pump energy into the system or out of the system, you can keep it isolated, it will come to an equilibrium. So, but then all you have to do is wait long enough. So, in that sense yes, yeah. So, in that sense you do not require energy to be you do not need to do anything other than just wait in order for the system to come to an equilibrium. So, they will come to an equilibrium and they will come to a common temperature. So, there is somebody else who is asking a different question, which says I did not get how trace is related to the canonical partition function. Okay. Yeah, so let me spend some time over that. So, you see what is canonical partition function? I think I understand the source of your confusion. So, you are probably wondering how I define canonical partition function as you have a system and then you have which is in thermal contact with surroundings. So, you have a system with this is U1, U2. So, then there is the number of ways in which you can rearrange the microstates of U1. So, this is your system. So, this is your reservoir. Okay. So, the number of ways in which you can rearrange your reservoir is this, but then keep in mind that U1 plus U2 is fixed, which is U. So, that means you can really think of this as omega 1 S U1. So, this is the number of total number of ways in which you can rearrange this system. So, the microstates of the system and the surroundings. So, so then this would be u minus u 1. Okay. So, now remember how we did this, we wrote this as e raised to s u 1, and this would so you Taylor expand this becomes omega 2 u e raised to minus u 1 into so you will get something like this. So, basically that is the origin of the so then you sum over all the u 1s. So, that is so that is how we define the number of ways in which you can rearrange the microstates. So, it becomes e raised to minus u 1 by t. So, this is anyway independent of the properties of the system. So, it is just the surroundings. So, that goes out, and then you have this. So, this is basically what trace means. So, this is your canonical partition function. So, this is defined as the canonical partition function. So, this is your microcanonical partition function. So, your omega 1 u 1 is the number of microstates, which is also called the microcanonical partition function, and then you multiply this by the Boltzmann weight and you sum over all the u 1s, you get the canonical partition function called z. So, this process is basically trace. So, in quantum mechanics what happens is that this gets interpreted as the degeneracy. So, if you have suppose u 1 is discrete, okay, suppose u 1 is something like n times h bar omega. Okay, so, if some integer times h bar omega, so then what you are doing is basically this is the number of ways in which you can rearrange the system, so that its energy, so that its energy is u 1. So, basically in quantum mechanics this is called the degeneracy. So, this is the number of quantum states which have the same energy u 1. So, the number of distinct quantum states with the same energy u 1 is called omega 1. So, in classical mechanics also there is something analogous to that, and that is what we have been calling omega 1 u 1, but in quantum mechanics it is much more familiar to us, and that is called degeneracy. So, basically that is how that is the reason why this is trace, because it is e raised to minus beta your E n times G n summed over all the states. So, all the states, so that there is a degeneracy of G n. So, this is basically trace of e raised to minus beta h, where h is your Hamiltonian. So, if you use your diagonal in your diagonal representation, that is what this is. So, this is how trace comes. So, it starts all the way from the classical picture, then so even though we use classical physics to derive this, but then this particular formula is applicable in general. So, even if you are talking about quantum mechanics, is the same formula, except that this gets reinterpreted as the quantum degeneracy, and so it naturally becomes the trace. And so that is also true when you are talking about quantum particles on a staircase. And so, remember that is how we started. So, we started this course from quantum perspective by looking at discrete energies and so on. A staircase is basically a quantum system, because you have discrete energies there. So, I hope that answers your question to some extent. Okay, so the earlier question has been rephrased. So, it says will the system use a part of its total internal energy in order to achieve the most probable microstate? So, remember that the first law of thermodynamics is never violated. So, that means the total energy. So, in other words, that if so long as you do not do any work. So, if you do not do any work, so in other words, so if say volumes are fixed. So, if volumes are fixed, then so long as no work is done, the internal energy is conserved. So, that means that the total energy before and after are the same. So, in that sense it will there will always be an increase in entropy. See, the point is that this is an irreversible process. So, what you are talking about, this mixing business, it is basically an irreversible process. So, you can't unmix. Once you mix, you cannot unmix. So, that the whole point is that this is irreversible. So, when you have an irreversible process, the entropy increases. So, there is no requirement for entropy to be conserved, unlike energy, which has to be conserved all the time. Entropy, in fact, does not have to be conserved. In fact, it never is conserved. So, most of the time entropy always increases. So, if you have if the combined system is isolated, it either remains constant or it typically increases. In this case, it increases. So, the system, does it use its total internal energy in order to achieve the most probable microstate? Well, I suspect not, because so long as no work is done, the internal energy before and after are the same, but still the entropy will increase. So, there that, see, remember that dq equals TdS is only for reversible process. So, if it is not reversible, then actually that equality is false. So, can I use the PPT again? So, I think that might be the source of the confusion there, that here the example that you have given me is basically an irreversible process. So, this so this is only for a reversible process. So, okay. So, this is reversible. So, what the example you gave does not obey this. So, this is so the example you gave is for irreversible. So, for irreversible process, delta S will always be greater than or equal to delta Q by T. So, it will so this is so for so this equality is only for, so this is for irreversible. So, if this if it is irreversible, the change in entropy is greater than this. So, in other words, even if dq is 0, so if no heat is pumped in and out of the combined system. So, you see the combined system, no heat is being extracted or inputted into the system, and yet the change in entropy is greater than 0. So, the net change in entropy of the combined system, that is because this process that you are describing is irreversible. So, if it is irreversible, the change in entropy is greater than 0, even though no heat flows in and out of the system. Okay. So, so the other so you see, so if in addition no work is done, then your internal energy by first law is still conserved. So, the total internal energy before is same as total internal energy after, and in spite of that, entropy still increases of the combined system. So, there is no connection between entropy, there is no theorem or a law which says entropy has to be conserved. So, in fact, the law says exactly the opposite. The second law of thermodynamics says the entropy always increases of an isolated system. Far from conserving, it actually increases. So, it is very unusual for the entropy to remain even constant, let alone we certainly will not decrease if it is isolated. Yeah. So, there is the other question which says the generating function you talked about in the very early part. Is this related to Green's function in perturbative calculation? So, you see, don't confuse, don't mix up unrelated issues. Um, the trace idea is basically a very general idea about how to deal with systems that are in thermal contact with surroundings. It is universally applicable, whether it is QED or whether it is many body physics, whether it is quantum, classical, it makes no difference. So, the moment you allow your system to thermally interact with the surroundings, that means exchange energy with surroundings, then this Boltzmann's idea is applicable. So, and so long as that system is large, so that fluctuations are suppressed, the canonical idea, the canonical partition function is universally applicable. It is unrelated to whether the underlying system is described by classical physics, quantum physics, whether it is a few body system, multi body, many body system, whether it is a field theory or it is anything else, it's universally applicable to all those systems. So, that is the power of statistical mechanics. So, there are certain very generic features that are applicable to all those systems. So, which is the reason why this course is so extremely important in physics, because pretty much there is no field, subfield of physics that is untouched by statistical mechanics. So, I hope that answers your question. So, are there any other questions? So, have I answered your question satisfactorily? The other, whoever asked the question. So, if you feel I have not answered your questions, please, ask again differently maybe. So, so are there any other questions? Are you satisfied with my answers? So, please whoever asked me questions, please acknowledge that I have answered to your satisfaction, because if you do not say anything, I am going to assume that I have answered your questions, but then it is also nice if you acknowledge that you are satisfied with my answers. Okay, so here is a question: if a Hamiltonian has only potential energy, can we still have temperature? Of course, we remember we did a problem on this. So, if you remember, there was a problem where we had a cube and there were electrical charges all identical stuck at the corners of the cube. So, because they are stuck, there is obviously no kinetic energy, but then there is potential energy because of electrostatic repulsion. And so, depending upon how many charges are there, so there can be a minimum of course 0, which is uninteresting, but you can have a maximum of 8 charges, because there are 8 corners of the cube. So, you can have fewer than 8, and depending upon that you have the electrostatic potential energy is different depending upon the number of charges, and as a result the entropy also differs as is a function of the electrostatic potential energy. So, remember we did that tutorial problem, which is very interesting, and so that answers your question. So, can we still have temperature? We remember we even calculated the temperature. We wrote it, there was a table which told you e raised to s versus u, and then therefore, s is a function of u. If s is a function of u, then there is a temperature, because temperature is nothing but the reciprocal of the slope of the entropy versus internal energy. So, I hope that answers your question. Okay, so the student who asked the question about the potential energy problem. So, there is a follow up which says that, but isn't temperature dealing with kinetic motion? Yeah, so you are right in the sense historically, when people thought about temperature, they were talking about gases. So, gases, of course, when you talk about gases, you typically mean ideal gases. So, ideal gas by definition has no potential energy. So, obviously, all the energy is kinetic there. So, whatever temperature is there is attributable to the entropy versus the kinetic energy, because that is the only type of energy that is available to a ideal gas by definition, because an ideal gas has no potential energy. But then the example that I gave in the tutorial is purposely the exact opposite of that, where there is no kinetic energy at all, because I prevent the charges from moving by pasting them to the corners of a cube. But then I have to make sure that there is potential energy, otherwise the problem is uninteresting. So, I make those the things that I have stuck to the corners, I make them have electrical charge. So, which means that they can repel and acquire electrostatic potential energy. So, as a result there will be entropy associated with that, which will be a function of the now the potential energy rather than the kinetic energy. So, yeah, so the blanket statement that temperature is related to the motion of charges is incorrect, because that stems from it's just a historical way of looking at temperature. So, temperature initially arose in the context of gases. So, certainly gases typically means ideal. So, ideal means only kinetic energy, but then as the subject of StatMech improved, I mean people understood more, then they realized that you can have various situations where you can have only potential energy also contributing to entropy and therefore to temperature. So, I hope you answer that answers your question. Okay, there is a next question asks how are Cooper pairs produced? Strictly speaking, that is not part of this course anyway. So, superconductivity is not part of this course, and but I can just roughly answer that they are not really produced, they already exist there. So, I do not know what you mean by produced, nobody produces them. So, it is just that the system you know, if you have a superconductor below the transition temperature, its you know, its ground state is basically is a collection of Cooper pairs which are non-interacting. So, they are already there, they are not produced. So, how exactly that comes about is of course, you know, something you have, there is something called the Bcs theory which you have to understand to appreciate what is going on. Yeah, so that is a that also, yes, Bcs theory also uses the ideas of statistical mechanics, but then that is a little bit more advanced than what I have discussed in this course. So, that would probably be something you should learn from your solid state physics course or advanced condensed matter physics course or something, but it will certainly, all those courses will use the tools that you have learned in this course. So, you will be pretty well equipped to understand those courses because you have taken this course, which is statistical mechanics. Are there any other questions? Okay, we have a question here that says, what is phase space in statistical mechanics? I believe I answered this question in the first live session. So, perhaps the student missed that one. So, again I am going to answer it again. So, phase space, the underlying system that you are studying, if it is classical, then the phase space refers to the collection of position and moment of all the constituent particles in the system. But if the underlying system is quantum mechanical, then the phase space obviously the collection of quantum states consistent with a given macro state. So, it is the collection of the quantum, basically the wave functions of the system. So, the next question is, if the resolution of phase space becomes infinitely small, do we still have degeneracy, or is it a quantum mechanical feature only? So, remember that degeneracy is not really a feature of quantum mechanics per se, because so we have defined the see this omega, the number of microstates is precisely degeneracy. That is what degeneracy is. Basically, is the number of different ways of rearranging the subatomic constituents of your system in such a way that the total energy is something given. So, that is what degeneracy means, even in quantum mechanics or in classical mechanics. So, it is unrelated to the laws that are obeyed by the constituents of the system. So, they are always I mean degeneracy is a very general concept. Okay. Okay, so there is another question here that says, if the total entropy can represent the feasibility of the process, why does Gibbs energy change is needed? I am not sure I understand the questions. So, one general piece of advice is that please do not reinterpret the concepts that I have been teaching you to mean something completely different from what I have taught you. Because in physics every concept has a very sacred, very fixed, precise meaning. You are not allowed to very casually reinterpret those notions to mean something else. So, whatever you have learned before registering for this course, you please forget about all that and focus on whatever I have been teaching you in this course, because entropy has a very precise meaning which I have very carefully defined and calculated in various contexts, whether it is classical or quantum. So, if you disregard all my efforts and go back to your vague notions that you may have imbibed through some other means, then you are not going to be benefiting from this course. So, it is important for you to leave your prejudices aside and forget about all the concepts that you may have learned earlier and focus on the concepts that I have taught you in this course. So, do not reinterpret what entropy means. I never said that entropy represents the feasibility of a process. I never made that statement at all, and yeah, Gibbs energy, I have precisely defined what it means. So, please do not put words into my mouth. I did not ask that question. I mean, I did not make such statements. So, are there any other questions? Okay, so there is a comment here that says there are some textbooks that follow combinatorics and factorials to calculate microstates and distributions. So, the question following that comment is it fully analogous to the way you calculate entropy using saddle point? Unless I actually look at those books and see what they are doing, I will not be able to properly answer your question, but my strong guess is yes. I mean, firstly, I did not invent this subject. Obviously, I also learned it from somewhere else, and that somewhere else is precisely those types of books only. So, if so, it is very likely that whatever I have taught is pretty much the same as what is in those books. For example, Patria also spends a lot of time doing combinatorics, not in the way in which I do it. He kind of does it somewhat differently. I start with examples, simple examples, and work my way towards more complicated situations. For example, I use the generating function method, the integral representation of the number of microstates, which is a combinatorial notion, but I think Patria does not do that. So, in that sense, my method is somewhat novel, but I am sure you will find, if you look hard enough, you will find it in many books, whatever I have explained, but I can't really pinpoint which particular book has whatever I have discussed in the early part of my course. But I will be grateful if somebody knows some particular book which discusses the that integral representation, that means that the generating function method that I have described. If you spot it in any particular book, please send me an email telling me which book that is. So, I will be interested in knowing that. Yeah, so the follow up comment says other books use Lagrange multipliers to optimize and calculate distribution. Um, Notice that that is precisely what I have done also, because you see the device of introducing the chemical potential, basically the integral representation introduces these auxiliary quantities called theta and phi. Those are precisely the Lagrange multipliers. So, eventually they take on the role of Lagrange multipliers, and they finally become the temperature, and they become related to temperature and chemical potentials. So if you notice from your those books that you have in mind, those Lagrange multipliers are also precisely those quantities that I just mentioned, namely temperature and chemical potential. So, my theta and phi that I have discussed in the early part of my course, they are precisely those Lagrange multipliers that you are talking about. So, it is pretty much the same thing. So, are there other questions? So, there are around 5 minutes left. So, if you have any further questions, comments, if you are not satisfied with my answers, you please send us emails, and we will answer them that way also. So, right now we have only a few minutes left. So, if you have any further comments or questions, please ask now. Okay, final question. What are the types of questions in the final examination? So, there will be a mix of relatively simple questions and some medium questions and some difficult questions. So, I will make sure that there is a kind of good mix between all three different levels of questions, and because I think the examination will be it will not be multiple choice, and we'll have to hand grade the answer scripts. So, there will be some theory type of questions also, meaning that which will involve some calculations. So, they will not all be multiple choice. So, we will be hand grading the questions. So, I will not be asking only multiple choice, maybe some of them might be, but be prepared for relatively detailed theory type of questions also. Okay, so we are about to close the session. So, I hope you do not have more important questions to ask. If you still have important questions to ask, you please send us emails. We will always be happy to answer them that way. So, thanks for your questions. Yeah.